Hey, so in the last video, we talked about EVT. Remember, EVT is the extreme value theorem. If f is continuous on A to B, then f has at least one min, one max on A to B. Ew. Okay, sure. Today, we talk about MVT. By the way, these abbreviations are College Board approved. MVT, the mean value theorem. And sometimes it turns out that our textbook just provides us with gems. Here's this one. The mean value theorem is an existence theorem. It tells us that the number C exists without telling us how to find it. We can sometimes satisfy our curiosity about the value of C, but the real importance of the theorem lies in the surprising conclusions we can draw. I just think that's an adorable sentence. It's in your textbook on page 200. You might want to go read it yourself. So here's what the mean value theorem says. It says if y equals f is continuous on A to B, and not just the continuous thing we've been hearing a lot of, but and differentiable on A to B, not including the endpoints, then there must be at least one point, and we're going to call that point x equals c, such that f prime at that one point is equal to f of b minus f of a over b minus a. Remember, this is slope, but this is also slope between 2 points. It's average rate of change. And over here, we have slope at a point. And so what we're saying is, or what the mean value theorem is saying, is that if f is continuous on the closed interval and differentiable on the open interval, there's going to be at least one place on A to B where the instantaneous rate of change and the average rate of change are equal, where the slope of the tangent line and the slope of the secant line are the same, therefore parallel lines. Okay? And believe it or not, I'm actually going to have the audacity to now completely walk away from discussing mean value theorem and go back to, what was that I read? We can sometimes satisfy our curiosity about the value of C, but the real importance of the theorem lies in its surprising conclusions we can draw. Yeah, and so that's what we're going to say here. We're going to say our focus today is actually all about the surprising conclusions. I mean, don't get me wrong, you will have a mean value theorem question on the AP exam. I'm almost willing to bet my favorite donut money. But the surprising conclusions, wow. Okay, so corollary number one, which by the way is the name for it only in our textbook, so don't bother trying to learn that. If f is continuous on A to B and differentiable on A to B, then when f prime is greater than 0, f is increasing on A and B. And when f prime is less than 0, f is decreasing on A and B. And this is going to be powerful for us, actually. Yeah, knowing, knowing about increasing and decreasing on f is going to be important. So, can we say something like, hey, if f of x equals x squared minus 3x plus 5, can I figure out where f is increasing and where f is decreasing? Okay. So, using our pre-cal or algebra 2 brain, we say upturned parabola, decreasing until I get to the vertex, increasing after the vertex, and then I use minus b over 2a to find the x-coordinate of that vertex. So minus b over 2a would be x equals 3x. Okay, and so then I see, okay, f is decreasing, f is decreasing on negative infinity to 3 halves, and f is increasing on 3 halves to infinity. And that's what we would say, and we would be thinking about this graphically. But now we're being encouraged to think about this using our calculus. And please make sure you use your calculus plan on calculus tests. Calculusly, I want to say something about f prime. Okay, so f prime in this situation is 2x minus 3. And I know f prime is never undefined, and there are no endpoints here. So I'm only going to be looking when f prime is equal to 0. And so I get x equals 3 halves. So I have x equals 3 halves. Well, let's build a little f prime sign chart and put 3 halves on it. And test the value over here, and test the value over here. In f prime. You'll notice that I start labeling these sign charts with what they are, because I want to remember where I want to plug stuff into. I don't want to plug stuff into f yet. In fact, generally the only time I want to plug stuff into f is when I want to know what is the value of a maximum or a minimum. Instead, I'm looking for right now, when is my f function decreasing and when is my f increasing? If I plug a 0 into f prime, I get negative 3. If I plug a 2 into this x value in f prime, I get a positive 1. And so what does this corollary tell me? It tells me that when f prime is positive, f is increasing. Here's f prime positive for all values to the right of this. And when f prime is less than 0, or when f prime is negative, then f is decreasing right there. F is decreasing from negative infinity to 3 halves. And I know that because f prime is less than 0. So this is going to be kind of really powerful for us in lots of ways. I can now say f is decreasing on negative infinity to 3 halves because f prime is less than 0 on that interval. And yes, you are going to have to write this justification, and that's part of why we've been writing sentences all this time. And I know that f is increasing on 3 halves to infinity because f prime is greater than 0 on that interval. Okay, there you go. Increasing, decreasing. Excellent. Now, we can know another thing. Here's our graph of f. Here's that point 3 halves. What's true here on f prime at 3 halves? Do you remember how we came up with that number? That was us setting f prime equal to 0. And 0 here. Now, let's think about what this means. when we see this and how that relates to the graph. This negative on f prime to the left of 3/2 is telling us the slopes over here are negative, and therefore f is decreasing. This plus sign tells us that on f prime, the plus sign over here to the right of 3/2 tells us that on f is going to be increasing. F is going to have a bunch of positive slopes over here. I actually want to talk for a moment about what's happening between decreasing and then increasing. So without seeing the graph and without comparing y values, I now know that I have a minimum here. I think it's pretty powerful. A minimum when f prime goes from negative to positive, f has a min. You know, there's an assumption here that f and f prime are continuous at that point. Okay. When f prime goes from positive to negative, what can we say there? Positive slopes, positive slopes, positive slopes, zero slope. Negative slopes, negative slopes, negative slopes. What's happening on f at x equals a if f prime goes from positive to negative? F prime represents the slopes of f. All these slopes are positive. F prime represents the slopes of f. All the slopes here are negative. What do we have as f prime goes from positive to negative? We have okay. We have f as a x. Okay. It's going to be important for us. Oh my god. So let's move on. We can now say that when we see f prime a plus minus, we have a max at x equals a. And if I see f prime plus minus plus, then I say f has a min at x equals, in fact, let's not get confused. Okay, and then f prime c plus plus. So here I understand that f is increasing until we get to this point. And then it stops increasing. And after this point, f is increasing again. Now, how do I know we stop at this point? Because I don't have this. This tells me that the whole interval, f is increasing. But when I see this, I see f is increasing. F is not increasing anymore because there's no plus there. And then f is increasing again. When does this happen? How about y equals x to the third? On this graph, f is increasing, f has a slope of 0, and then f is increasing again. So if I don't have a sign change, I don't get a min or a max. Mins and maxes only occur when f prime has a sign change. So what about endpoints? Okay, so here's f prime, and I see plus, and this is a. So A is my right endpoint. There's nothing over here. And I know that f prime is positive to the left of that point. Well, this tells me that f is increasing until I get to that point. And so I know this to be indication of a max at x equals a. And if I have this on my f prime sign chart, a negative f prime tells me that f is decreasing, and so I'm decreasing until I get to x equals b. So this is an indication of a minimum at x equals b. So that takes care of the right endpoint possibilities. We've also got some left endpoint possibilities. C minus f prime. From this point, f prime is negative, which means from this point, f is decreasing. F is decreasing. So that tells me that this is max. And then finally, if I have a plus there, and this is an f prime sign chart, because f prime is positive, f is increasing. F is increasing from this point. I don't know if it's increasing like that. I don't know if it's increasing like that. I don't know if it's increasing like that. All I know is f is increasing. And therefore, since this is the left endpoint, and my function is increasing from that point, this must be a min. So this is going to be a min on f at x equals d. Okay? Now, I kind of want to, yeah, no, I'm going to wait on that in a different minutes. But it's something the college board told us. So, corollary 2. Functions whose derivative is 0 at every point are constants. And, you know, once you sort of get to that place where you're comfortable with where you're comfortable with what these words are saying, you realize that, so you're saying that if I have this horizontal line, y equals 4, and I take the derivative and get y prime equals 0, if my function has a derivative that is always 0, that function must be a constant. Yeah, I agree. Sounds very, very obvious. So let's not spend any more time with corollary 2 and move on to corollary 3. Functions with the same derivative differ by a constant. Okay, now what does that mean? Well, here, take a look at these three. Y equals x squared, y equals x squared plus 2, y equals x squared minus 5. So what's y prime over here? Well, y prime here with our shortcut is 2x. And what's y prime here? Y prime with our shortcut is 2x. And here, yeah, y prime equals 2x even there. So functions with the same derivative, these functions, not their derivatives, these functions all differ by a constant. Okay? And so what we're seeing here is whether I'm talking about my reference graph y equals x squared or some vertical shift up or down of that reference graph, the derivative is always the same. Now, for us, that's like, okay, yeah, so, but for us for next semester when we're going backwards, when we're starting with a derivative and we're trying to build the original function using anti-differentiation, this is going to be hugely, hugely powerful for us in January. So there's a whole lot of stuff that I'm getting here when I talk about uh, this mean value thing without even actually using the mean value thing, which we'll do in the next video. I do want to say antiderivative. And let's introduce this word right now. So if I know, for example, that y prime equals 6x, then I'm going to say that, oh, look, there must have been a 2 up there that came down to make that 6, right? Because when I take the derivative of this, that 2 comes down. But look, it's not just 2 there, it's 6. So what must be here originally so that when I bring that 2 down, I get that 6? Yes, a 3. So there's my antiderivative, but wait. The antiderivatives all differ by a constant. And so any time I go to make an antiderivative, and you're going to be making so many of them next semester, anytime I go backwards, I'm going to have that plus c. And it's a constant, it's knowable. I'm just going to need another piece of information, like an ordered pair to plug in for x and y to solve for c. All right, but don't forget the plus c on the derivatives. All right, so, and I guess I could say, big F is the antiderivative of little f if big F prime equals little f. That's how we're going to be thinking about antiderivative moving forward. But at this point in my notes, I've got some antiderivative practice. I kind of wanted to go back to that other stuff, but I think I'm going to trust me and say, okay, f prime equals 12x squared. Will you please tell me what f, not f prime, what f might be? Did you get 4x to the third plus c? So how did I do that? Well, I said, look, my derivative is a 2. I must have brought a number down, 3. And so 3 times what gives me 12? 4. So, and when you're not sure, you can always test by taking the derivative. Bring the 3 down, multiply, subtract 1. Don't forget when you do an antiderivative to have the plus c. So then what if I had something like f prime equals 1 over x plus secant squared x plus negative 1 over x squared plus 1? Can you tell me what f could be? Thank goodness we remember all our derivatives. And if we don't, hey, you need to know these. Can't do second semester without knowing your derivatives. Okay, whose derivative is this? This is ln's derivative. Whose derivative is that? Well, that's tangent's derivative. And whose derivative is that? Whoa, that's cotangent inverse's derivative. And what's still missing? Don't forget the plus c. Okay, antiderivatives. You gotta know your derivatives, folks. Okay, let's go back and do a little practice with our corollary one. How about g of x equals x to the third minus 12x minus 5. Now I know that g prime would be 3x squared minus 12. And so, using g prime, what can I say? Well, you know, I can say that g prime equals 0 when x equals plus or minus 2. And how did I do that? Well, I said 0 equals 3x squared minus 12. 12 equals 3x squared. 4 equals x squared. X equals plus or minus 2. Okay? So these are my g prime critical numbers. So there's a negative 2 and 2. And let's have some test points. And let's remember, this is a G prime sign chart, not a G sign chart. So I'm going to plug these test values into G prime. If I plug a 0 in there, I've got a negative. If I plug a 3 in there, I've got 27 minus 12, that's positive. If I plug a negative 3 in there, it gets squared, I still get 27 minus 12 is positive. And so what do I know? Well, suddenly, because of the mean value theorem, I know, oh my goodness, a ton of stuff. I know that G is increasing on negative infinity to negative 2 union 2 to infinity, because G prime is greater than 0 on those intervals. Right? I'm not only writing the answer, but I'm providing the justification of this statement. That's what I'm really looking for when I'm saying write a sentence every time. It's not really because I care about the sine of pi over 6 is 1/2. It's because when we get to this, that writing a sentence is an expectation. What is it that I'm saying? When does it happen? And why does it happen? I want to see all that information. Okay, but we can go further and we can say G prime is decreasing on negative 2 to 2 because G is decreasing because G prime is less than 0 on negative 2 to 2. Great. But wait, there's more. We talked about what would happen when we had a sign change from positive to negative on G prime. As long as G and G prime are continuous, and I see this sign change, G prime goes from positive increasing to negative decreasing, I know that there's a max at x equals negative 2 on G, because to the left of x equals 2, negative 2, G prime is greater than 0, and to the right of x equals negative 2, G prime is less than 0. So that seems like a lot of writing. However, here is a 4-page letter that every calculus teacher in America received some years ago, where College Board changed its mind. They used to accept this sign chart as evidence of maxes and mins. Now AP readers are told you don't even see a sign chart. So the test taker must say this: I need this for every max and every min for the rest of the year. I need, anytime you're asked to find a max or a min, that you write this justification sentence. There's a max, where, on what function, because I've got to have that justification. Right? So what would the justification sentence look like for what's happening at 2? Well, when G prime goes from negative to positive a few minutes ago, we said that we would have a minimum. So I'm going to say there's a min on G at x equals 2, because to the left of x equals 2, G prime is less than 0, and to the right of x equals 2, G prime is greater than 0. I must have that justification sentence. Just hit every min and max for the whole rest of the year, unless it's a multiple choice problem. You need to be writing that justification sentence. Okay. Now, with that in mind, I'd actually like to move us in another direction. We said that G was x to the third minus 12x minus 5. And then we said that G prime was 3x squared minus 12. But I'd like to talk about G double prime. G double prime is 6x. Now, let's think about G double prime sign chart. Where is G double prime equal to 0? Well, that's equal to 0. And if I plug in a number over here, I get a positive. And if I plug in a number over here, I get a negative. What's happening on our graph as x at x equals 0, or as we go from negative land into positive land? Okay? What's happening on G there? And what's happening on G prime there? Okay? Let's take a look. Pull out my calculator and see what my graph can look like here. I've got x to the third minus 12x minus 5 times 12. My graph of G seems to look like this. Now I know that's, and that's not the x-axis. X-axis, because that's minus 5, is up here. So what do we have here? This is an important thing. G is increasing and then decreasing. I see a maximum there. G is decreasing and then increasing, so minimum there. But I'm thinking about G double prime. G double prime being negative. G double prime being positive. So what's that going to do? Well, what's my function look like until there? And what's my function look like after there? And so what I'm going to say is, because G double prime is less than 0, G is concave down. And because G double prime is greater than 0, G is concave up. Concave down, concave down, concave down, concave down, concave down. Stop. Concave up, concave up, concave up, concave up. A G double prime sign chart tells us about concavity. And this point here, where G double prime goes from negative to positive, or for that matter, positive to negative, this point where we have the sign change, this is called an inflection point. Okay? So, suddenly, we've got a whole lot of stuff to talk about. Okay? G double prime equals 0 and x equals 0. We need that. But that doesn't necessarily guarantee us an inflection point there. For example, if I have this, I'm concave down, and then I'm concave down. And at this point, G double prime is undefined, because I couldn't take a derivative there. So there's no way I could take a second derivative there. So this is G double prime, negative, negative. No inflection point there. Our inflection point is a place where the function, in this case G, changes concavity from concave up to concave down, or from concave down to concave up. An inflection point is a point on the function where the function goes from concave up to concave down, or concave down to concave up. All right. So I got an inflection point at 0, but I only know that because on other sides, I have that sign change. Okay, we have a G prime sign chart here with negative 2 and 2. And we said minus, plus, plus. So with these two sign charts, suddenly I have a huge amount of information. Okay? This sign chart tells me that there's a min on G at x equals, was it 0? Oh, this is the G double prime. There's a min at x equals 2 because to the left of x equals 2, G prime is less than 0, and to the right of x equals 2, G prime is greater than 0. Now, look, I know that there are a number of you who say, you know, if I start with that and then just say to the right, G prime is greater than 0, yeah, believe it or not, this isn't sufficient. Because just because somewhere on the right side G prime is greater than 0, yeah, well, not necessarily where I want it to be, and that's why I have to say here. Okay, I have to have all this information. Just like when I'm talking about the max at x equals -2, because G prime is greater than 0 to the left, and then G prime is less than 0 to the right of -2. Okay? But what else do we know? Well, we know that G is increasing on negative infinity to -2, being into the infinity, because G prime is greater than 0 on those intervals. And we know that G is decreasing on -2 to 2, because G prime is less than 0 on -2 to 2. Okay? So that's all the information we get from this. But now we've got concavity and inflection points as well. And we say, oh, look, a sign change in G double prime. So we say G has an inflection point at x equals 0 because G double prime changes sign there. You can use that. A few years ago, you couldn't use that. You can use that. Or you could say because, and this is sort of more in line with the defense we wrote for justification we wrote for mins and maxes, or because to the left of x equals 0, G double prime is less than 0, and to the right of x equals 0, G double prime is greater than 0. Some people actually like this. It's a little more writing than saying that G double prime changes sign at x equals 0, because this is remarkably similar to the max min justification. And so some students feel like there's less that they have to sort of hold in their brain. But in addition to that inflection point at 0, I can also say G is concave down on negative infinity to 0, because G prime is less than 0 on negative infinity to 0. And I also know that G is concave up on 0 to infinity, because G double prime is greater than 0 on 0 to infinity. Wow! I mean, just so much stuff. And now look here. Remember back in chapter 1 where I would tell you about increasing and decreasing, and I would tell you about concave up and concave down, and I would say, hey, draw that graph? Well, guess what? Now we have the way of getting all that information so that we can put things together to talk about, well, what's this graph look like in the age of I can't graph it on my calculator. And yeah, we could actually still put you in that position. We won't very much, but yeah. Okay. Yeah, so here, to go back, we would say here's G information, and here's increasing or decreasing, and here we have concave down, and concave up. And so we've got -2, 0, we've got 2, and to the left, G prime is positive, then negative, then positive. And here we see that G double prime is negative, and then positive. And remember, we talked about saying, okay, if the function is increasing and concave down, it looks like this. And then we're decreasing and concave down. Oh, and don't forget, as we change from increasing to decreasing, we have this. And now I get to 0. Now I get to 0, and I see I'm decreasing, but I'm shifting from concave down to concave up. And so I recognize that as an inflection point. I'm decreasing until I get to x equals 2. After x equals 2, I'm increasing and concave up. So I'm concave up from 0 on, but from 2 on, I start increasing. And because my g function goes from g prime is negative to g prime is positive, I know that I have a min here. And I didn't actually plug these x values into g to determine what was going on. Instead, I used this stuff that we reviewed in chapter 1. So now we actually have this really powerful method of using first and second derivatives to help us create graphs. And that's pretty powerful. Right. The only thing we haven't talked about with this now is endpoints and inflection points. Let's think about that. If my graph looks like this, and I get this endpoint, I see concave down, concave down, concave down. Is that an inflection point? I know it's a max because it's the highest point in its neighborhood. I know it's a max because f prime is positive, which means f is increasing until we get to this point. Right? Isn't that how we said max? And you could write that justification by saying there is a max on f at x equals a because to the left of x equals a, f prime is greater than 0, and f and x equals a is the right endpoint of x. Okay? It's a little different than our normal justification because we have an endpoint. Our slopes aren't coming from both sides, only from one side. Okay. So, I can't know inflection possible at an endpoint because I can only ever approach from one side or from one side. And in order to have an inflection point, I need to have a change in the second derivative at that point. I can never get a change at an endpoint. So, no inflection points at endpoints. You can have maxes and mins at endpoints. You can have inflection points at interior points, but no inflection points at endpoints. And some people will actually claim that this year. So please don't. An inflection point is where I go from concave down to concave up. That change in concavity can happen here. I could be concave up, but then do I change to concave down? No, it's an endpoint. So endpoints can never be inflection points. All right. Let's have you do this one. F of x equals x to the third minus 2x squared on -1 to 2. And I want you to do everything. I want you to tell me of any maxes or mins. I want you to tell me when f is increasing or decreasing. I want you to talk about f being concave up or concave down. And I want you to talk about inflection points. And I want you to write justification sentences for each of those things. Yeah, so pause the video and get to work, because we're going to be doing a lot of this. Hey, welcome back. All right, so I'm going to say f prime equals 3x squared minus 4x. If I factor an x out, that's 3x minus 4, which tells me f prime equals 0 when each of these factors equals 0. So if I build an f prime sign chart, populate it with 0 and 4/3, and then I plug a value in like 1, I get a negative, -1, negative plus negative is positive. And over here, if I plug in a 2, I got 4, 12, minus 8 is positive. And so from this sign chart alone, I can say all kinds of things, right? This is an f prime sign chart. Remember, AP readers don't see that. So don't expect that because you write that, I know where you think there's a min or a max. I will, though, say f has a max at x equals 0 because to the left of x equals 0, f prime is greater than 0, and to the right of x equals 0, f prime is less than 0. And yes, it seems like a lot of words, but really it's only one sentence. It's just a very, very, very clear sentence. What about mins? Well, I feel like I can say f has a min at x equals 4/3 because to the left of x equals 4/3, f prime is less than 0, and to the right of x equals 4/3, f prime is greater than 0. So did we take care of all of our mins and maxes? No, because look, we're on a bounded interval. I have an endpoint over here at -1. I have an endpoint over here at +2. So look what's happening here. F is increasing because f prime is positive until we get to x equals 2. That means I have a max there. And here, -1, I see f prime is positive after -1, which means f is increasing. And if f is increasing after -1, then that's a minimum. So I got to justify those as well. And I'm going to say there is a min at x equals -1 on f because x equals -1 is the left endpoint, and to the right of x equals -1, f prime is greater than 0. What about over here? Okay. There is a max on f at x equals 2 because to the left of x equals 2, f prime is greater than 0, and x equals 2 is the right endpoint. I will tell you that on the next test, many, many, many people lose points because they forget to check the endpoints for maxes and mins. Please, not just derivative equal to 0, are places where we could have mins and maxes, but also endpoints. All right, so we talked about mins and maxes, but I can also say f is increasing on -1 to 0, union 4/3 to 2, because f prime is greater than 0 on these intervals. And then I could say f is decreasing on 0 to 4/3 because f prime is less than 0 on 0 to 4/3. Right? So all that information comes from my first derivative. What about inflection points? Okay, so if f prime is equal to 3x squared minus 4x, then f double prime would be 6x minus 4. F double prime equals 0 at x equals 2/3. So I set this equal to 0, I added 4, I divided by 6, and then I reduced. Okay, so here's my F double prime sign chart with 2/3 on it. If I plug in a 0 here, negative. If I plug in a 1 here, positive. I have a sign change on F double prime, so I know there's an inflection point at x equals 2/3. So what can we say here? We can say f is concave down on negative infinity to 2/3 because f double prime is less than 0 on negative infinity to 2/3. And I can say f is concave up on 2/3 to infinity because f double prime is greater than 0 on 2/3 to infinity. And then I can also say f has an inflection point at x equals 2/3 because f double prime changes sign there. Yeah. You can get away with that, or you could say f double prime has an inflection point at x equals, I'm sorry, f has an inflection point at x equals 2/3 because to the left of x equals 2/3, f double prime is less than 0, and to the right of x equals 2/3, f double prime is greater than 0. You can use that sort of modified max-min justification for yourself there as well. Oh my goodness, that was a lot of stuff. So, yeah, I just want to look at 2 more problems with you here. I know we're getting to that place, but these are problems that do what we were doing, but they have sort of distinct algebra to them. All right, so with this situation, I know f prime, I have to use the product rule. So e to the x times x squared minus 4x plus this times the derivative of that, which is 2x minus 4. Okay? And I want to set f prime equal to 0, but wait a moment, I should do some factoring. And so I'm going to have e to the x squared minus 2x minus 4. So this is the f prime I want to set equal to 0. Now, funny thing, that is never equal to 0. Right? Think about that graph. E to the x never equal to 0. So this part of f prime, this isn't going to give me any critical points. This will, and this isn't factorable. Luckily, I know quadratic formula. And so I could actually get those points, right? So we've got 16 and 4 is 20. 2 plus or minus 2 root 5 over 2, which is 1 plus or minus root 5. And no, really, I mean, we're expected to do this without a calculator because we've had years. 1 minus root 5, 1 plus root 5. And this is my f prime sine chart. And so if I plug in something here, like 1, right? Because 1 is that center, and then I'm going to the left, root 5, and going to the right, root 5. So I can plug a 1 in, positive, minus, minus. This is always positive, so negative times positive is negative. Root 5 is a little bigger than root 2, which is 2. 2 plus 1 is 3, so if I put in a 5 over here, what's going to happen? Well, this is always positive. 25 minus 10, 15 minus 4 is 11. That's positive. And what about here? 1 minus a little more than 2, negative 3. This is always positive, so don't worry about that. It's going to be 9 plus 6 is 15 minus 4 is 11. And so now I've got my f prime sine chart filled out. And now I'm ready to talk about a max here and a min over here and talk about f increasing and then decreasing and then increasing, and all that's good. So then we come to f double prime. And again, I have product rule. X squared minus 2x minus 4 plus this times the derivative of that, 2x minus 2. And again, I need to factor out that e to the x. And so what do we have now? These cancel. We have x squared minus 6 times e to the x. Well, this is never equal to 0. This will be equal to 0 at plus and minus square root of 6. And so now I can do plus or minus square root of 6 on my f double prime sine chart. And plug some values into my f double prime. This is always positive. Something in between would be 0. That's going to be negative. Bigger than square root of 6 is square root of 9, which is 3. 9 minus 6, that's positive times positive. If I plug in negative 3, negative 3 times negative 3 is still 9, minus 6 is still 3, times a positive is positive. And so now that I see all this stuff, I can say, oh, look, there are inflection points at negative root 6 and positive root 6 because f double prime changes sign at those points. And I know that f is concave up from negative infinity to negative root 6 and positive root 6 to positive infinity because f double prime is greater than 0 on those intervals, and because f double prime is less than 0 between negative root 6 and positive root 6, I know that f is concave down. Okay. So that's a lot of stuff. You should also be prepared for this algebra, which we've already kind of seen. How do I deal with finding derivatives here? Well, again, we're looking at product rule. Plus x times f. Factor out the smallest power. What are we left with? Minus a minus 1/2 is going to give me 4 plus x. All of this comes out. I still have the 1/2x. So 3 halves x plus 4 and 4 plus x to a negative 1/2. Here's my f prime. You can move this into the bottom. That might reinforce that when x equals negative 4, you don't exist, right? Because you're under a square root and you're in the denominator. But this definitely makes me think that I've got domain restriction here. I see that f prime is equal to 0 at negative 8/3. Okay. And just to go back up here, what happens if I plug a negative 5 in here? Well, I'm going to have square root of negative 1, which is no bueno. So I think my original function is going to have an undefined slope at negative 4. But nothing to the left of negative 4 is going to exist. So there's negative 4, there's nothing to the left. This is f prime. We've also got this negative 8 thirds. Okay, so let's try out some values here. If we plug in negative 3, it's going to be 1 over the square root of 1, which is 1. Negative 3 is negative 9 halves, which is negative 4 1/2, plus 4 is negative. And if I plug in something 0, I'm going to have 4 on top, and on the bottom, I'm going to have square root of 4 or 2. So that's 4 over 2 or positive. And so here's my f prime sign chart. Look, I see a min here at x equals negative 8 thirds. Oh, what do we have here? Don't forget to check that endpoint. There's a max at x equals negative 4 on f, because x equals negative 4 is the left endpoint, and to the right of x equals negative 4, f prime is less than 0. Right. I don't know. Do you see it? Do you feel it? Like, all these years of math, all this practice that felt crazy and disconnected is now all showing up as, oh my goodness, it's all coming together. I needed to do this so I could set these derivatives equal to 0 so I could find when f prime was undefined or when f prime was equal to 0. Even evaluating functions at points that we started doing in middle school becomes this thing that we do all the time here. We're so dependent on that knowledge. And by the way, we didn't do f double prime here. And on a test, yeah, I feel comfortable saying, no calculator, draw that graph. And how would you draw that graph? You'd find the mins, you'd find the maxes, you'd find the increasing, you'd find the decreasing, you'd find the inflection points, you'd find the concave up, you'd find the concave down. And that can give you very, very close to a perfect graph. So I would practice those last two for, I would definitely practice those last two for their algorithmicness. But there's a whole lot of stuff that you seem to need to know here. And as our textbook says, the real importance of the theorem lives in the surprising conclusions we can draw. Have a nice day, everyone.